Perfect.
Thank you.
Thanks very much. So I would almost say the presentations yesterday were almost too good, because I got back to my hotel last night and looked at my slides and I was like, not quite as pretty as some of the ones that were presented yesterday. Particularly the Puma and the Harden ones looked awesome. So yeah, great job for those who worked on those. So my name is Ian Pegler. I'm part of the computer-aided engineering team at NVIDIA, and specifically I'm in the developer relations group. So my role really is to kind of help people that are building engineering applications, simulation applications, use and leverage the NVIDIA platform. I'm originally from the UK, live in Chicago now. And I want to try and give you kind of an overview of like what NVIDIA is doing to accelerate product development and simulation. So I'll probably spend some time talking about what our vision is and some of the underlying technologies that hopefully will enable that vision. And then I'll show some examples of some of the developers we work with and some of the cool things they've done. And it was really great to see quite a few of those developers are actually going to present today. You know, you've got NTOP, Neural Concept, Physics-X, companies like that we regularly work with. So yeah, let's get going, and hopefully this will be entertaining and educational for you all. So pretty much every NVIDIA presentation starts with a slide like this. And the reason we start with this slide is really, you know, NVIDIA is a platform company. We don't make any tools. Like, you can't get an NVIDIA tool to do anything. And you know, if we ever develop any tools, then you're probably going to end up having a pretty uncomfortable conversation with Jensen at some point about that. So the idea is that we develop this platform that people build on, and they build their tools on top of that platform, right? So we're really aiming our platform for developers. And what is that platform? Well, I think most people know, right? NVIDIA make chips, and you can see those along the bottom. So GPUs, CPUs, chips that go in our networking products. I think some people don't realize we make CPUs, so CPUs are important, just as GPUs. There's certain things that CPUs are very good for. And then obviously we take those CPUs and GPUs and we assemble them into larger scale systems. You see the GB, NVIDIA naming is quite something. So you see the GB200 NVL72 SuperPod, which is basically our AI supercomputer. So it's basically acts as 72 GPUs acting as one big GPU, which is super important for these larger and larger, more complex AI models that people are developing. And it turns out it's also really useful for doing simulation and engineering workflows as well. And then on top of the kind of hardware is the software layer. One interesting thing about NVIDIA is we have more software engineers than we do hardware engineers. So they make things like the underlying drivers for the hardware, software libraries, which I'll talk a little bit more about, and then also application development frameworks as well, which I'll also talk about. And this is the part that hopefully makes it really easy for developers to actually develop on our platform and make really, really cool tools. Right. So this is probably I think the most important slide in the presentation in some ways, because it kind of talks about where I think we're going with simulation and where our vision is. So my background is, I think I said, I spent most of my career as a CFD engineer before joining NVIDIA, so I'm kind of a simulation guy with a simulation background. And for a long time, I think people have talked about this idea of being able to explore the design space, right? Instead of just running 4 or 5 different designs, can we run thousands and thousands of designs and really explore the design space and hopefully find some good ideas and optimum places for us to go with our product design? But that's been somewhat limited, right? Because if you're designing an aeroplane, right, there's only so many complex simulations that you can run in a given time. On this chart, we've said got several per day for a CFD simulation. Which is great, but you're never going to explore the design space with that. But the next step up is, okay, let's take what you're doing today in simulation and just run it a lot faster. And that's what what a big part of my job really is, helping people move their simulation code from just being CPU to running on GPU, to get these kind of orders of magnitude speed up. And hopefully, being able to run these codes a lot faster will also help us generate more data. So if we're going to do any kind of training of AI models, we can actually leverage this accelerated compute to run these models a lot faster. And then hopefully then we can do thousands of different combinations per day. And the dream's always been to do these like design space, optimizations, multidisciplinary optimizations, where we can have all of these disciplines and kind of really understand where to go with design, and hopefully using some of these surrogates will get us there. So I'll come back to this in a little bit more detail. I'll talk a little bit more detail about the accelerated compute side and the AI physics side a little bit later as well. So where are people today? And I mean, I think that probably some of the people in this room are probably a little further ahead than I maybe give people credit for in this slide, but often I work with a lot of large companies, and the truth is a lot of them use simulation as what I describe as being like a virtual test. So what does that mean? Well, basically they're doing virtually what they did in a test environment, but just virtually, which is good, right? You're saving time, money, compared to doing physical test. But it's almost like, somebody in the company will come to me and go like, I'll run a simulation on this thing, give us the results, and they'll go away with those results, just the same way as you would a test. But the problem is you're not really using the simulation to actually find a better design, or really, it's not the simulation engineer's not going actually, hey, let's tweak this and go in this direction. They're just giving the results back. And that's where honestly a lot of companies are today. That's how their design processes work. So what we really need to do to really make the most out of simulation is move people to actually, have simulation-driven design, like, use things like a joint, which I think some people talked about yesterday, or topology optimization to actually let simulation drive the design to a better place. And I'll eventually get to this place I was talking about, the multidisciplinary design exploration, where you bring all of the different fields together to actually hopefully, get a truly optimized design. But obviously there's a lot of barriers to getting there, right, to move to this thing. Some of them are obviously cultural, and some of them are just being able to run these simulations in a cost-effective way to enable, the massive increase in simulations you need to do, right? More HPC resource, and also to run these things faster. And that's a big part of, where we're going with accelerated compute, right? If it takes 3 weeks to run a simulation, and it does for some of these very complex cases, and your design cycle's 4 weeks, then really that simulation is not really going to affect the design too much. So hopefully that gives you an idea of like where my head's at about where we can help accelerate this move to more simulation based design. So what I thought I'd do now is talk a little bit about some of the underlying technologies that NVIDIA we offer. Again, these are mainly aimed at developers rather than end users. So like nothing we develop, you're going to get a little GUI that you can like click on and stuff like that. It's really like you're going to GitHub to find the code and use it like that. So for a lot of people, our customers are developers that are going to take these libraries and integrate them into their own software. But if you're a keen hobbyist and you want to have a play around, then you're more than welcome to obviously go. A lot of this stuff is open source and freely available. Go and have a play around with some of this stuff. So I'll probably kind of go from the top: Warp, CUDA-X. I probably won't talk about NIM. I'll talk about Physics NEMA. I'll talk about Omniverse. So let's start with Warp. Let's talk a little bit about what Warp is, because it's kind of interesting. And some people earlier in the sessions were talking a bit about using Python, so I thought it'd be a cool thing to talk about. So fundamentally, Warp is basically a way to write CUDA kernels, but basically in a Python framework that's very much optimized for simulation. And you can kind of see some of the simulations that have been generated by Warp. So sometimes to write kind of these kind of types of codes directly in C++ in CUDA is kind of a heavy lift for someone that's not maybe got a computer science background. But Warp's quite nice because you can use Python. A lot of the data structures that you would need are already built in, so you can access mesh type functionality. There's access to like a lot of it is backed by VDB, which we'll talk about a little bit in a minute. So it's a great way to kind of, if you're interested in writing sort of simulation tools, to use the Warp framework. And we actually have had people kind of develop, and Autodesk of research have done some work to actually take it and actually build simulations on a large scale. So this is a CFD simulation of New York. and it's a very large scale, so 26 billion cells. So leveraging again the kind of power of what we can offer as far as a GPU compute to do these extremely detailed, extremely large scale simulations. And actually brings me something I probably forgot to mention at the start, is one of the challenges, to be honest, we have sometimes is like with the scale of compute and what we can do today, it's actually sometimes just changing people's minds about the scale of simulation they can do. So many people are used to doing their like small scale simulations, a couple of million cells. And really with compute you can do today, you can massively increase the fidelity in a number of cases you can do. So often it's changing like people's expectations of what you can do with simulation. I kind of put this in yesterday just because someone mentioned that they'd used VDB for some of their projects. So we actually offer something called Nano VDB, which is actually this kind of framework for dealing with like sparse volumetric data. So VDB's background, it comes from the visual effects world, and we've kind of used it now for actually doing simulation as well, because it's a really nice way to get data, like simulation data, this sparse data onto a GPU. And the Nano VDB is a smaller version that's optimized to run on the GPU, and as you can see some examples there. And it's kind of embarrassing actually. You see Ken Muthes, he kind of developed it to the style. I didn't actually realize he was the guy that did it for ages. I worked with him on a project for ages, and I was like, this guy knows a lot about this. And it wasn't until like a year later that I went on the website and I saw he was like the chair of the whole like thing. Okay, so that's a little bit about Warp. Next thing I want to talk about is CUDA. So CUDA is probably one of the key reasons for NVIDIA's success in the last few years, right? Is it's this way to take the GPU and actually write general purpose programs that leverage the GPU. So that's what basically CUDA did, right? It was this language for writing programs to run on the GPU. So obviously we still massively support that, but one of the key things we offer with CUDA is a whole bunch of libraries, right? So that's why I call it CUDA-X, because CUDA plus all the libraries that go along with CUDA. And again, these are like optimized libraries with the idea to make people's life very easy that want to develop applications on our platform. I won't go through all of these, but there's some kind of interesting ones. cuDNN, the first one, is probably one of the key ones for us. Q is a way to accelerate deep neural networks, so obviously very important for all of the AI applications. PhysicsNeMo, I'll talk in more detail about that. That's our framework for developing AI surrogate models. cuOpt is an optimization library. So a lot of people are using it to for path planning, like you see a little robot going around the warehouse, what's the optimum way to kind of, like the traveling salesman type problems, right? What's the optimum way to do a certain number of tasks on the path? One other one is CuPy-Numeric. So again, someone mentioned yesterday they were using NumPy. So CuPy-Numeric is kind of interesting because it's not really a CUDA library as such, but it's actually a drop-in library. So if you're writing Python and you want to actually have that run on the GPU, and you're using NumPy, you can just go in and replace NumPy with CuPy-Numeric, and then all of that will then run on the GPU. So it's kind of a nice drop-in way to actually kind of accelerate if you're writing Python applications. What else have we got here? We got cuDSS, which I will talk a little bit later. So there's actually a whole ton of libraries that are super useful for simulation. Some of them are here. So I won't go too much depth to all of these libraries, but when you're writing simulation tools, there's certain things you do a lot of, right? And often it involves solving systems of matrices for both, CFD, finite element analysis, electromagnetics. I mean, fundamentally, there's a lot of matrices that you've got to solve. Either you're going to solve them in a direct way, or you're going to use an iterative approach. So we do have libraries to do both. So we have cuDSS, Direct Sparse Solver, cuSparse, and AMG-X as well. So I'll talk a little bit about those. So most people maybe from the CFD world are familiar with the AMG approach. So this is, again, solving systems of matrices. So we have a library in NVIDIA to do that and do it efficiently on GPU. So one thing I would say about our libraries is the idea is that you can use this library and don't have to worry generation to generation that you're optimizing it for the next generation of GPUs. You can just use a library and know that this is going to run as fast as it can. cuDSS, so this is the library to solve direct sparse solvers. So this is commonly used for structural type problems that you want to run on a GPU. And what you can see is the whole range of different problems that we've tested, and at the high end, the biggest problems we can get like 60x faster. And that was really a whole story about GPU that I'll talk about later, is like GPUs like big problems. Like if you've got a tiny little simulation, like GPU is probably not going to like help you that much. What really, where it really shines is these big, high fidelity problems, because it really gives the GPU enough work to really show its benefit. And another cool thing like CUDA-X does, for example, I forgot to mention, is like underneath it's actually got a ton of different methods for actually solving these sparse matrix problems, and it's actually got an AI algorithm that will look at what you give it and pick the best algorithm. So it's not just one approach, it's actually a range of different approaches that's used underneath. Next on the list, I'll talk about Physics Nemo more in a bit. I've skipped NIM because it's not really that interesting, and we'll talk about Omniverse now. So Omniverse is kind of this like framework, again, another framework for developers to kind of build digital twins and do that within a photorealistic environment. And quite a few of our kind of developers have already kind of integrated it into their platform, like ANSYS are going to have it as part of their like next generation fluids tool, so you can see like a photorealistic version of the vehicle behind there, and I'll show a little bit more about that in a minute. Neural Concepts, who are going to present later, used it and integrated it for this SP80 racing yacht that they have been working on. Again, I won't say too much, so they may talk about it later, but again, you kind of can generate these really cool looking photorealistic images. Also, Siemens integrated it into their Teamcenter X package, because I don't know how many people have to deal with PLM on a regular basis, but one of the challenges with some of these legacy PLM tools is when you've got huge bills of material like the size of that ship there, being able to visualize that in a photorealistic way is almost impossible. So they've actually integrated Omniverse to allow them to kind of visualize like a whole ship. And I've got a video I can show later of that in a bit more detail. So far I've kind of gone through some of the key technologies that are now, like we developed to enable simulation. And what we did actually for the supercomputing conference last year is we actually put a demo together where we tried to actually just show all of them working together to give people an idea of what kind of things you can create. So if you go to build.nvidia.com, you can actually go online and find this demo, and it's kind of cool. We basically did a CFD analysis on a whole bunch of different vehicles, and then we trained a Physics Nemo AI surrogate model, and then we connected up Omniverse to do this cool visualization. So it's a nice interactive way you can kind of play around here and change the vehicle. You can interactively move around these streamlines that you see. And it just shows you the power of leveraging accelerated compute to generate the CFD, leveraging AI to be able to like infer this in real time as you change the vehicles and change the ride height. You can change the wheel types. I've got some other cool videos actually that look nice. And you can also do it in like a really nice photorealistic way, which looks really, really nice. So if you're collaborating with designers, you can do it in a nice, nice pretty way. And it's funny, these vehicles are actually supposed to be generic, but anybody that knows anything about it, that looks dangerously like a Ram truck. So I showed this video to guys from Stellantis like last week, and I was like, this is a generic vehicle, and they're like, no, it's not, it's a Ram truck. And I was like, yeah, it does look exactly like a Ram truck. And so this is, this has been a cool way to kind of just show people like what the power is if you use these latest technologies, because sometimes simulation and these tools can get kind of stuck in the past, right? So, trying to leverage these latest technologies can really improve the user experience and how accessible they are. And sorry, this is a lot on this slide, but it does actually show all of the different pieces that went into that demo. So, you've got the Physics Nemo part that's connected to, in the middle, connected to the kit application. That's basically Omniverse, the pretty window you see. And then you can see the data delegate, which is actually converting a lot of the CFD data and things like that into that nano VDB format, so we can like work on the GPU in a very efficient way and visualize things. We're actually using Warp to do these, like streamlines are actually Warp based. So that the Warp's actually doing the calculation. So again, that's where we're leveraging Warp. So again, it just hopefully shows you a combining of all these different things. And like I say, you can go to build.nvidia.com and have a play around with it. It's also called a blueprint. We have this concept of blueprint, so you can actually download all of the code underneath that. So if you wanted to like use some of this stuff for your own application or use case, you could actually download it and then like build your own application off of it. And that's always what we want people to do, right? Is take this stuff, integrate it into their own application and build something really cool based on our platform. And the other thing I'd say is, like, obviously we develop all these tools, but really it's up to the developer to pick what pieces they want to use. Like, we never insist that you must use every single thing from our portfolio. Like, some developers just use one thing. They might be, Physics Nemo is really cool. We're going to use pieces of that. Or we're going to use Omniverse, but we're going to develop our own thing because that's our own IP for doing one part of it. So, you know, we're very flexible. We don't force anybody to use everything, basically. Right. So we're back to this picture again. So I wanted to talk a little bit more detail about these two last things, because these are the newer areas, I guess, you know, the accelerated compute and the AI physics. So I'll talk about accelerated compute a little bit, and then I'll talk about AI physics, and then I'll show some videos, and that should hopefully be about right. So accelerated compute then. So this is basically running a lot of simulations on GPU rather than CPU. So when I joined NVIDIA, I was obviously a CFD engineer, and like people were saying, oh, it can run like loads faster on GPU, like, you know, it's these 40x, you know, orders of magnitude faster. And I guess the question I never really understood is why? Like, why is it so much faster? Like, what is it about GPU that makes it particularly fast? And the analogy that's often used when we do our like introduction to CUDA training courses is this comparison between a car and a train, with the car being the CPU and the train being the GPU. And, you know, so imagine like right now you want to go back into the city, right? Want back over to Manhattan. You could either drive or you could take the train. And if it's in the middle of the night when there's nothing on the road, the car's probably going to be the quickest way, right? There's no traffic, you just drive straight over. It's the quickest way. But as more and more people obviously want to drive into the city, that road's going to get more and more clogged. And eventually it's going to come very, very slow. So at that point, it's actually probably going to be more efficient to move people into the city is actually to use a train. And as long as the train's running very regularly and you can fill that train with people, it's a very efficient way to move things. And that's kind of like what the GPU is. It's this kind of way to do, it's like a throughput machine. It's got a ton of memory, it's got a ton of cores. So if you've got to do a lot of the same thing at the same time, it's extremely powerful. And you can imagine the architecture has always been built for that, coming from the days of graphics, right? Fundamentally a GPU, you've got to paint all of the pixels in the screen at the same time. So yeah, this analogy actually is pretty accurate. And sometimes the actual clock speed of a GPU is lower than the CPU, but it can just do so much in that clock cycle. So hopefully that kind of makes some sense, but it's actually pretty good. But one of the hard parts of actually GPU programming sometimes is actually keeping the train full. You've got to keep, especially with the newer GPUs, keeping enough work on the GPU to keep it busy is actually sometimes the hard part. So let's just talk a little bit more about the hardware then. So on the left is like a classic, kind of more classic PCI GPU, right? The thing that you'd put in your desktop. And on the left side there is the kind of data center GPUs, which are more commonly used for like the AI side. And to be honest, the GPU is actually not really the right name for it, right? Because you can't really actually use those for graphics. But the kind of GPU name's kind of stuck. So you'll see different generations of GPU. Hopper, there's Blackwell, and there's before Hopper there was Ampere. So there's always like a new generation of these data center GPUs every year. And the key thing is just looking at the memory bandwidth increasing and also the memory. So every generation we put more memory bandwidth, and this basically means you can run bigger problems on the GPU faster. Generally a lot of simulation is very bound by the memory bandwidth. How quickly can I get from the memory to the GPU? And we get this really high memory bandwidth with these data center GPUs because we're using this HBM memory. And if you see there's that little picture of the GPU here, the key thing with these GPUs is the memory is like mounted right next to the GPU. So this is the HBM memory, this is the GPU. And this is what gives us this really, really high bandwidth, but it's kind of a more expensive process, this CoWoS process to mount the memory onto the GPU But that's really a key part of why we can get this super high performance. And you don't get it on these desktop GPUs. Generally, it's more traditional, like DDR type memory. But the problem is, like, obviously for some people, they're like, oh, that's great, but these things are really expensive. And yes, they are. Like these data center GPUs, you know, these are hundreds of thousands of dollars to get systems. So, you know, sometimes it's hard to get access to them. But with this RTX Pro 6000 Blackwell, again, a catchy name, I know, it's really cool because we just brought this out. It's got 96 gigs of memory on it, so you can run some really big problems on it. It's got 1.6 terabytes of memory bandwidth, so obviously not as big as these ones, but you can actually, just in a workstation these days, do some really cool stuff with that GPU. So that's a lot more accessible, I think, for a lot of people to run that GPU, so you can do some really cool stuff on it. So we try to make a range of hardware, right from the really high end down to like your, you know, developer on their workstation playing around with things. I mean, you know, we strongly believe that a lot of the innovation really comes from people on their desktop, you know, who can run CUDA on their local GPU. That's really where a lot of innovation starts. I mean, even when you look at AI, right, when they start with AlexNet and the image recognition competition, that was just like some students playing around with some gaming GPUs where they could run CUDA. So, you know, it's a key part of where a lot of innovation starts for us. Just a little bit more about the hardware. I think I talked about the big rack systems earlier on, these systems where there's 72 GPUs in a rack for these really large AI models. All NVLink together. You can kind of see the back of the NVLink. Oh, you did give me a laser, didn't you? There we go. You can see the back of it, which is all NVLink together here. And the memory bandwidth on this connection actually is enough memory bandwidth to actually handle the whole of the internet traffic at once. It's massive memory bandwidth on the back of these systems. Some other things that are kind of cool though that we come out recently, I don't think I put a slide in about it, but the DGX Spark, I don't know if you've seen that, so it's a really cool little desktop AI development system that's kind of like a mini version of one of these big systems. So, you know, you can run like a 200 billion parameter model on that, so it's a really nice way, you know, again, to increase that accessibility to this kind of technology. Okay, I'm going to skip this slide. And again, on a yearly rhythm, there's always much to our engineering team's probably disbelief. We moved to a 1 year rhythm of new GPU generations. So obviously at the moment we're on Blackwell, and then Rubin is coming. I think they've just got the first systems in the lab, and then Fryman's coming as well. So always something coming. Cool. So we're still talking about the accelerated compute side. So I've just talked about a little bit of a background to the actual hardware that we use, and now I'll talk about some of the like outcomes of running some of these tools on GPU. So we did actually a lot of work recently with BMW. So BMW traditionally ran their external aerodynamics simulations on CPU. So we worked pretty closely with them to test some of their models, and we continue to actually work quite closely with them to run on GPU. So we showed that, you know, by leveraging GPU, we can go from like, you know, hours to kind of 20 minutes for some very large cases. Like the case you see there is almost 500 million cells. It's in a big external aerodynamics model of a race car. And we can really get that down to like being tractable in like the minutes time frame from potentially days for some of these cases. And it's kind of nice they actually posted about it on their social media, which was nice. And that's, I think, the picture that was on the program this year. So it's kind of a cool story. And we continue to work closely with those guys to move more of their simulation workload onto GPU. We're actually working with them at the moment on thermal management, because thermal management is actually kind of a tough problem because you've got the external aerodynamics, plus you have to model the interior of the engine bay as well. So you have like loads of geometry inside that engine bay because you're modeling all of the thermal properties of the things heating up and cooling down. You've got to run it for long transients. So some of the simulations to do this can actually, if they do the full fidelity simulation, can actually take 7 days to run this on a pretty decent HPC system. And like if they can get it down to 2 days, they'll actually do that in production. That'll be part of their regular production work. So getting this kind of high fidelity simulation faster does have a real effect. Similar slide actually from ANSYS Fluent, another big CFD code. Don't worry about all of these different graphs, they're not really that important. The key one to think about is actually this one. So that this is running this 250 million cell aerodynamics case on 12,000 CPUs here. That's 12,000 CPUs in it, and it's 17 times faster than running on the 512 CPUs. But if we run it on just 8 H200s, we're 34x faster. And you can kind of see that kind of graph starts to level off. So you'll probably actually never get to this 34x faster than 500 cores. And this is why this is so cool, because 34x faster is significant, right? Like that's like game changing for a lot of people. Similar, we've worked with Cadence have got a code that works really well on GPU fidelity. Another use case that's like kind of cool is in aerospace. These high lift configurations when you're basically coming into land, or you're normally in this high lift configuration where the landing is down, the flaps are extended. To really accurately capture this, you really need to run these very high fidelity LES, capturing the real time transient behavior of the flow field to get the right numbers. And again, to run that is extremely expensive. But again, if we run it on GPU, you can see there we can do it. I mean, GB200 was like 40, 50 times faster than a CPU node. But then if you often the argument people come back with is, oh yeah, it's super faster, it's a lot faster, but it's a lot more expensive. And you're like, yeah, it is. Like a GPU node is a lot more expensive than a CPU node. So that's why the graph down the bottom, we kind of normalize by the cost to say, if you spent the same money to get that performance, we could do it like 7 times cheaper, basically, with GPU. Similar story with this, but I just like this. I don't know if you can see it, but it's really cool. You can see like the flow pattern on the fan blades there. And we continue to work on a lot of different use cases to accelerate them. And one of the things you'll see is actually, this is a really important area for Jensen. So often, this was from the keynote he gave at DC 2 days ago, and there's often CAE and engineering simulation examples in there, because it's like it's an area that really interests him. Okay, let's talk about the AI physics side. So this is the area where there's definitely a lot of interest at the moment, and it's an area that's rapidly changing. I think every day I see someone's come up with a new model architecture to try and use AI approaches to predict things. Some of the examples I've shown you predict flow fields, predict structural problems, predict electromagnetics. And by the way, even though I've shown a lot of CFD examples, because I'm CFD biased, because that's my background, some of this stuff is also equally applicable to like electromagnetics, structural simulation. Structural is a little bit more fussy though, but yeah, it's not just like CFD. So again, similar to what we do generally at NVIDIA, right? We've built this framework called Physics Nemo to allow people to kind of take that framework and build AI surrogate on top of it. And on the right there, you can kind of see the different approaches that you could take. I mean, you can just use PyTorch, right, and just build your own thing from scratch. At the other end, you could just buy someone's software for it. So for most people, that's actually going to be the best approach for them. Everyday CA engineers, they're not going to develop their own software. They're going to work with one of our partners like Neural Concept, Physics-X, Beyond Math, companies like that, to actually leverage the software directly. But hopefully for a developer, it's going to be easier to build on top of PyTorch with Physics Nemo than it is going to be to build on PyTorch alone. So that's hopefully what we're going for, right? Just to make the developer's life easier. And Physics Nemo itself, we've put together a lot of pieces to hopefully make it easier. And part of that is obviously a lot of the underlying plumbing you need to actually bring in CFD data, get it into the right formats for training, be able to train on multi-GPU, multi-node. A lot of that stuff's already done, so a lot of people can take that and just integrate into their own tools. We also actually build model architectures as well, and I'll talk about one of them in a minute. So NVIDIA research, we often task them with looking at new things, difficult problems, so they help develop new model architectures to actually come up with architectures that can efficiently be used for more of these physics applications. Some of the applications we've done, you can see here, there's a lot of different ones. I'd probably point you to the top right-hand corner. This is really where Physics Nemo started. It was actually internally, we used it for a lot of our own cooling analysis. So that's actually one of the gaming GPUs in a box. Also weather prediction, that's a big area for us. There's a separate project called Earth 2 where we're working to actually come up with a model to predict weather and upscale like weather data as well. Also, one thing I would say about some of these approaches, though, is sometimes people, they kind of see it as an and/or approach, right? Like, it's like, oh, this is going to replace, so we go back to this slide, right? This is going to, CFD or AI physics, but it really isn't. They're going to complement each other. I strongly believe that. Like, I feel like, we've already seen some companies, for example, actually Ford did a presentation on this at GTC a couple of years ago, where they're actually using the AI surrogate models to initialize the flow field, so they can actually run their traditional CFD solvers a lot quicker because they're starting from a really good first guess. There's often there's submodels that are used in simulation. Can we use an AI surrogate for that submodel and integrate it with the traditional solver? And then obviously there's just using the AI surrogates from scratch to do sort of the design optimization. So I feel that it's not quite a clear cut, like, this is going to replace that. That won't be the case. In the same way I think about the testing, right? Like, the CFD hasn't replaced the wind tunnel. And that's because there's still a lot of value in what the wind tunnel can give you, right? And you might use it a little bit less for more of the final validation stage, but there's still value in that. And I expect a similar pattern to emerge with these technologies. So I've got 5 minutes left, so I will, which actually is pretty good actually. I'm actually relatively on time, so that's good. So I'm going to flick to this slide. So this is a slide of someone that's actually integrated PhysicsNeMo. So SimScale actually integrated it into a tool to actually do pump performance. So they have a lot of customers that use their platform to simulate pumps. So they have a lot of pump data, and they've developed a way that you can quickly get a pump curve, or at least an estimate of a pump curve, by integrating PhysicsNeMo under the hood to generate these surrogate models. And this is exactly what we want, right? An end application that under the hood's powered by one of our frameworks. Luminary Cloud, they actually use PhysicsNeMo, and they've actually done this where they've kind of integrated it into, I think this is Blender, and they, you can, within Blender, you can put a design in, and then you can just infer and get like a rough, idea of what the drag's going to be. So again, giving that early, quick feedback. And then we obviously work quite closely with NTOP, who a lot of you are already familiar with. And they've done some cool stuff, integrating PhysicsNeMo as well. Sorry, I skipped the video there. It's always tough when it's YouTube. Anyway, you can kind of see the idea, right? You can kind of quickly change the geometry in a robust way, which is what they're really good at, and then quickly infer, get an answer, and then move on to the next design direction. Another big thing we're working on is actually generating more data. I mean, one of the issues with using these approaches is you need training data, and the training data is expensive, right? So we do work to produce different training sets that people can use to train the models, and we'll continue to kind of support those efforts and open source these training sets for people to go and use. Okay. So that was kind of coming to the end a little bit of what I had to present. Just to talk a little about exactly what I do in developer relations. I particularly focus on working with a lot of the small and startup companies in this space, which I really enjoy because often a lot of the innovation comes from those companies. So day to day, I do a lot of work with the companies to help get access to some hardware to do testing of the software they're developing on the latest hardware if they want to benchmark. Giving access to some of our experts internally. A big part of what I do is work with some of our dev tech people. So if you're developing something and you want to make sure it's running the fastest it can on GPU, then we have specialists that can take a look at profiles, which is there. That's actually from Nsight Systems, really dig into the details about how your code's working on GPUs and make suggestions about the best way to optimize it. We also work closely with our Inception team, which is our program for startups. So if anybody's in a small company, they're not part of Inception, I'd recommend joining. You can get some discounts for GPUs. Also, it actually gives access to NVentures. So I work closely with our venture capital arm, NVentures. So we often fund a lot of companies in this space. if they're using our platform and we think it's a good fit. And obviously we also like to celebrate success, right? That BMW story was a great one, right? You know, leveraging GPUs, Siemens, you know, integrated into their software, and then BMW getting some real benefit and real value out of running these things on GPU. So we're always keen to promote these kind of cases, and you know, I often help with webinars and things like that. This is with Flex and Compute, who you heard from yesterday. Cool, I'm probably exactly at time, so just I'll end with this slide again. So I think the main messages to take away are, you know, we're developing this accelerated compute platform to make everything go faster, from just your traditional simulation tools, also to leveraging AI approaches. And really, you know, hopefully our platform makes it really easy for developers to make these kind of next generation tools. And like I say, my role is to help developers in that process by connecting them with the right people in NVIDIA. So, you know, please come and have a chat, you know, if you're in this area, and happy to help where I can. So with that, I'll leave it there. Thanks a lot.
To see the full recording of this and previous presentations, as well as information about future CDFAM events, visit cdfam.com.